So let's start with the filtering. Normally, if we want to extract points from images, we need to use an edge-segmented image. So let's see how we detect edges in images. I think you saw this already, but the solution is to use a convolution. The convolution is a very important mathematical operation that we use in images, and you have probably seen this before. The idea of a convolution is very simple, is that I'm processing this pixel here, and to process this pixel, what I do is I take into account the neighbors of this pixel, and I take into account this mask that I apply here. This is the filter I'm applying, and this is my original image. And the things that I compute, I'm going to use them to get the value of this new image. So this is the original image, I never touch it. This is the processed image, and this is where I am going to put the numbers. And the only thing we're going to do is just, I take this value here, and I multiply this value times the pixel that it's under it. And I add this to the value of this part of the mask times this pixel times plus the value of this part of the mask times this pixel, and I keep doing this all the time. Once I have done all these operations, I have done a convolution. And then this provides a result that I'm going to write in this pixel here. And then I'm going to shift the mask. And this means that the mask is going to be in this position now. So I'm going to process these pixels here. Okay? And this is going to be the result for the central pixel another time. So if we look at this as a function of time, I have this mask that it's going across the image, and then in every position I'm going to place the mask and multiply the value of the mask times the pixel that it's under it, plus the value of the next one, and so on. Okay? So that's a simple convolution. So how do we filter images with this? It depends on the type of mask that I use. I could use, for instance, a mask like this one here, and this is a low-pass filter, which means that essentially what I have here is an exponential, which is e to minus x squared plus y squared. Now, many times you have seen a single exponential like this, which is e to minus x squared. If I do it in 2 dimensions, if I create a mountain, in this case, this is the equation that I should get. Okay, and this part here is just a normalization. Okay, it's to prevent my result to go out of the values of the dynamic range of my image. So it's 1 over 2 pi times the variance of my Gaussian. So in this case, this is the standard deviation. So sigma square is the variance. So an example of this, a very widely used example, is this mask here. Why is this used very often? Because imagine that I have a 1 megapixel image. I need, for every pixel, I need to do 1, 2, 3, 4, 5, 6, 7, 8, 9 multiplications and 8 additions. Okay? So and I need to repeat this 1 million times for every pixel in my image. So this means this is a very time-consuming operation. In this case, you see, multiplying by 1, it's something that I don't need to do, so it's just the value. Multiplying by 2 in binary is just shifting 1 position. Multiplying by 4 is shifting 2 positions. So this is a very fast mask to apply. And if I want the dynamic range of the image to remain constant, the sum of all the weights in this mask should be 1. And for this to be 1, what I need to do is to divide the result by 16. And again, dividing by 16, because 16 is the sum of all these weights here. Okay, I'm going to just erase them all. If you sum all these, you're going to see that what we have is 16. And then 1 over 16 is what I apply after doing the convolution. So I apply these values for the convolution, and then the result I divide it by 16. And this is 4 shifts in the opposite direction in binary. Okay, so this is a very efficient way to compute a Gaussian. But you could have Gaussians of any size, windows, the masks, this is an example, 3 by 3, but it could be bigger, and you could have any values. How do I do a high-pass filter? So this was a low-pass filter, so I'm smoothing the image. How do I detect high frequencies in the image, things that are salient? So normally what you do is you apply masks. In this case, the weights of the mask do not sum to 1, they sum to 0. And in this case, I could get out of the dynamic range, so I need to do some normalization after applying the mask. And this will be a mask for detecting vertical edges. You see, what it's doing here is saying, okay, for this pixel, how different are the left neighbors from the right neighbors in this pixel? Okay, and you apply one mask, and this is detecting vertical edges. And then you apply this second mask, which is looking at horizontal edges. It's saying, okay, the neighbors, my pixel neighbors that are on top, how different are they from the neighbors that are in the bottom of the image? So, this is called Prewitt. This is a well-known mask. And this one here is called Sobel. And in this case, you see, the only thing we're doing is just, okay, this neighbor here, if this is my pixel and I have a neighbor here and a neighbor here, and this distance is 1, and this distance is 1, this distance is square root of 2. So let's say that this neighbor is closer to this one than to this one. Okay, so every pixel, this pixel is closer to this pixel than to the other one. And then what this mask is doing is saying, okay, I take more into account the pixels that are closer. This is why they have a 2 here. But you know, you could apply any mask. In fact, some of the well-known methods like SIFT is just taking, you know, for looking for horizontal or vertical edges, it's just looking at how different is my pixel on the left from my pixel on the right. And just if you use these elements that are off a little bit in the diagonal, you're just you know, applying some noise reduction, in fact, and you're being more robust to noise and outliers. So these are some examples. This is my input image. You see, we apply this low-pass filter, and then you see that here the image is a little bit sharper, and here we have made it a little bit blurrier, but we have reduced noise too. So the reducing the noise comes at the price of reducing also the definition of the contours in the image. And then in this case, I'm applying this approach of taking the left neighbor minus the right neighbor, and I detect vertical edges. You see the result of applying this is this. Mathematically, I would write this as the partial derivative of my image, I of xy, with respect to the x direction. So I'm looking at how my image is changing in this direction. Okay? Remember that an image, this is the x, and this is the y. And normally, in the image, you have the 0, 0 here. Okay? So if I take the transpose of these, which will be this, and I apply a convolution with this mask, what I get is this image here, which is the partial derivative of my image with respect to the y direction. How is the image changing in this direction? And this is why I find these horizontal edges here. Okay? And then how do I build the gradient image? The gradient image is basically the combination of the partial derivative with respect to x and the partial derivative with respect to y. And I do it like this. So the partial derivative of my image is, so the derivative of my image, in fact, is just taking the derivative in the x direction plus the derivative in the y direction, and then I square them, and I take the square root of all this. Okay, and this is what is giving me the derivative of the image. This derivative of the image is known as the gradient image. We should make a difference between what's a gradient image and what's an edge image. The gradient image is computing for every pixel how the image is changing, how similar is this pixel to its neighbors. Okay, that's the gradient image. If I'm in a place where high gradient, this means I'm in a contour, or I'm in a place where several edges come together, or a very textured part of the image. If I'm in a boring white area of the image, or if this pixel here, for instance, has very little gradient, okay? But the edge is just applying a threshold to the gradient image. So the only thing I need to do is, if to this image I say, okay, all the pixels that are smaller than 100 are going to be set to 0, and all that are bigger than 100, from 100 to 255, if I'm using 8 bits, are going to be set to 1. And then what I get is the edge image, okay? So it's important to make the difference between the gradient image and the edge image. When we want to detect or to detect interest points in images, we are going to use the gradient image. We're not going to use the edge image. Okay, we're not using a binary image, we're just looking at the gradients. So many times I'm going to talk about the derivative of my image with respect to x and the derivative of my image with respect to y. And I'm going to use the following notation. Instead of writing all this thing here, what I'm going to write is ix. This is the derivative in x, and I'm going to write iy, and this is the derivative in y. Okay, the partial derivative of my image I with respect to y. Okay?